scale invariant. So, as you can see, right, there are a bunch of them in terms of we saw the huff, then we saw blob detection, then we saw corner detection, we saw edge detection. Now we are looking at something like scale invariant feature transform. Again, the goal is the same. Goal is again the same, that we want to be able to match features across images, and then based upon the draw some inferences, right, either about the geometry or about the mutual transformations between the images and so on. So, this is a very kind of popular among the ones right, that the ones that exist. I mean, this is the most popular, by the way, and this is due to David Loewe, and it came as a conference paper in '99, and then came in a journal in 2004. And of course, again draws a lot heavily from what we have seen till now in terms of the log, right, what we saw in the last class, right. So, draws heavily from what log can do, but then right, this person, he proposes a bunch of things along the way, some of which are intuitive and some of which may not be that intuitive also, but yeah, the point is it works, right, and it's not like deep learning, okay. It works because there's a lot of kind of a systematic thinking that's gone into it. I mean, sometimes, right, some things they assume, which I think we just have to accept, right. I mean, that's just a compromise between computation and accuracy and so on. Okay, now the first thing, right, that we want to do is the difference of Gaussian, which is dog, right. This, I think, at some point of time I had said that, right, this is something that will come up again. Okay, difference of Gaussians. So, we want to sort of establish a relation between difference of Gaussians and the scale normalized log. Scale normalized log. The scale normalized log, of course, right, we know what it is. And it turns out that actually you can of course the advantages are that log is far more easier to implement. It just requires two Gaussians with different sigmas. A lot more easy to implement than actually a log. And it turns out that there is actually a good so there is an approximation there, but still in practice it works very well. Okay, and we will see what that is. So, in order to do that, right, let us first look at what is this. The first thing, which is, let us say, g of x, we will take a Gaussian, 1D again, okay, and then we'll I mean, whatever happens here happens there in 2D, minus of x square by 2 sigma square. Okay, now let us first look at dou g by dou x, okay, in this case, okay, let us say dou g by dou x, which turns out to be 1 by root 2 pi sigma into e raised to power minus x square by 2 sigma square. Because it is with respect to x, we will get minus 2x, then maybe 1 by 2 sigma square. So, this we can write as minus, what is it, 2 will cancel off, and then minus 1 by root 2 pi sigma cube x into e raised to power minus x square by 2 sigma square. Okay, I do not think we need this bracket. Minus 6. Okay, then let us look at second derivative. So, this is minus 1 by root 2 pi sigma cube x into e raised to minus x square by 2 sigma square into minus 2x 1 by 2 sigma square plus e raised to minus x square by 2 sigma square. And something that I had said last time, right, I think if you if you are attentive enough, right, you will see that something that I had asked you to prove comes out of this, by the way. I won't tell what it is, but I leave it to you to figure that out. So then you get minus 1 by root 2 pi sigma cube, and let's pull out this e raised to power minus x square by 2 sigma square, and then we will get 1 minus, what is this, x square, this 2 and 2 will cancel, right, x square by sigma square. Now let us kind of look at this one, right. So till now we have not examined what is dou g by dou sigma. See, till now whatever this one a derivative we have taken, right, we have always taken with respect to x or y, right. Suppose we examine this Gaussian with respect to sigma, okay, then what will you get? You will get 1 by root 2 pi, and then you have like, what is this, 1 by sigma into e raised to power minus x square by 2 sigma square. Now what will it be? Minus x square by 2, and then what is this, minus 2 by sigma cube, huh? Minus 2 by sigma cube. And then what is this, plus you need this e raised to power minus x square by 2 sigma square into minus 1 by sigma square, right. This is dou g by this guy, right, this equation 1. If you try to, right, find its derivative with respect to sigma, minus x square by 2 minus 2 by sigma cube plus e raised to minus sigma minus 1 by sigma. Okay, now, and if you do 1 by root 2 pi, let us just simplify this, okay. Okay, e raised to power, let us first pull this out just to clear the mess. Then what happens, 2 and 2 will cancel, we get x square by sigma power 3, right, x square by sigma cube, sigma 4, sigma power 4 in fact, and then we get minus 1 by sigma square. Or if I pull out minus, then I get minus 1 by root 2 pi, and then I can pull one sigma square extra, because this guy also has sigma square, and then e raised to power minus x square by 2 sigma square, and then you will get 1 minus x square by sigma square. It just confirm that everything is going on okay. So you get minus 1 by root 2 pi sigma square, 1 minus x square by sigma square. Yeah, okay. Now it's interesting, right? If you compare, let's say they call this expression number 2 and call this expression number 3, then you see that the second derivative, right, dou square gx by dou x square, if you see, that almost has a similar form, right, except that you need a sigma, right. So you need a sigma to multiply dou square gx by dou x square, right. So you can write dou square gx by dou x square is equal to this guy, dou g by dou sigma, right, where here it is a function of sigma. So this is actually called the heat equation or something, but this is nothing to do with image processing, okay. But anyway, turns out that this is also useful for us, okay. Now what you can do is, now here is where a certain amount of approximation goes, until now it's okay, right. Now what I do is, so this dou g sigma by dou sigma, okay. So what you have is sigma dou square g by dou x square. In fact, from now on, I am going to simply write this as this one, del square f, which is a Laplacian. The same thing will hold good, okay, dou square f. That is also the reason why I said that you know, see, a Laplacian will then involve an x square plus y square by sigma square, right, and which will also come here if you do this with respect to sigma. So, the 2D is just straightforward. Then this, right, so the way, right, this is written is, you write this as your g of sigma, not dou g by dou sigma. So, this you write as g of x comma y comma k sigma minus g of x comma y comma sigma by k sigma minus sigma limit, what do you think, k tending to 1, right. This is what it will be actually, or in other words, right, you can actually transfer the sigma onto the left and you will get sigma square delta square f is equal to limit k tending to 1 g of x comma y comma k sigma minus g of x comma y comma sigma by k minus 1. Now, it turns out that, see, on the say left is your scale normalized log, right. This is what we saw last time. This is what gives you a scale normalized log, and we saw what is the use of that, right. I mean, it allows you to catch the extrema and all very well, right, without kind of damping the magnitude of the strength. On the right hand side, right, now this what basically people have found is that this, right, they directly approximate it as g of, so what they do is, so this they directly approximate as simply a dog, which is a difference of Gaussian, and k, strictly speaking, right, k should be very close to 1 for this equality to be kind of meaningful. But in reality, what is found is the range of approximately equal to simply a difference of Gaussian, which means that you can simply say g of x comma y comma k sigma minus g of x comma y comma sigma, and it is approximately equal to a difference of Gaussian, which is what dog is, right. You just take one Gaussian, subtract it from the other for a reasonable range of values of k. Now, this is where this is kind of empirical. Strictly speaking, that is what should hold, but in practice, right, it turns out that k all the way, so a typical value of k that people use is, value of k is actually k is equal to root 2, okay, which is like 4 or something, right. Now, strictly speaking, that should be 1, but it holds very well. In fact, you can plot this and see yourself, okay. I mean, I would encourage you to plot this for different values of k and compare with a log on the left. Turns out that, it's, in fact, people go all the way up to 1.6 and all, there is a range of values where it works very well, okay, and this was known, okay, this was known, this is not related to the paper really, this is not like, Lowe found it or something, this was known. But then what he did was he exploited this in a very nice way. So, last time, right, when we saw log, right, we had sort of a scale space, right, where he said that we will convolve with right, different sigmas, and then right, depending upon whether the structure is coarse or fine, right. For smaller sigmas, the finer structures, right, will fire, and then for coarser sigmas, right, the coarser structures, right, will fire for larger sigma, right. What he did was the following, right. So, because computationally, right, I mean, after all, right, all this had to be done in a very fast manner, right. For example, OpenCV will have a SIFT implementation that can be run in 1/100th of a second or something, milliseconds in fact. And all that is happening because of these approximations and all that have been made, and to show that, right, it still remains reasonably robust and so on. And the way, right, he does this is as follows. I mean, he does a bunch of things, right. I will go through one by one. So, first thing, right, that he actually does is that he builds up what is called a dog scale space, right, instead of a log, instead of in the log domain. So, then what would you do? And of course, he chooses k equal to root 2. So, what that means is the first one image, right, that you have is actually blurred with sigma, okay, and then the next one, because you want this approximation, will be actually k sigma. And then the next one will be actually k square sigma, then you have k cube sigma, and then let us say k power 4 sigma. I mean, this again, how many how many images should you, okay, this is called an octave. I will tell you what that octave means, but for the time being, let's keep that aside. But let's say, right, if you did not have a, a pyramid or something, and you simply wanted to search through all sigmas, right, at a sort of, at a, what do you call, at a particular, this one, spatial resolution, right, a spatial resolution, that is, which is the highest kind of, say, resolution that you have, which is the image size, right. This is all at the image size, by the way, right. So when I say I apply sigma, that means that I take the image, I just apply at that spatial resolution. So it's like the highest resolution, right. That's what you have. An image is captured at whatever highest resolution you have. When you have a pyramid, you will downsample it, right. But here, as of now, there is no downsampling. These are just, the same image taken and then blurred successively. And what would you next? What would you do next? I mean, the obvious thing to do would be to actually catch the extrema, right? Because after all, that's what you want to know. I mean, right? So the coarser structures and the finer structures, you want to catch them. So then, what would you do? You would take these two, because now is where the dog comes into play, because now you are no longer using a log, right? You want to approximate it using a difference of Gaussian. So what you will do is you will actually subtract these two, right? That's what we said here, right? And you will subtract these two, and let's call this as dog 1. And then you will take these two, subtract them, you will get dog 2. And then you can take these two, you can get dog 3. In fact, in his paper, he goes up to dog 4. Okay, by the time that you are at dog 4, how much is your sigma up by now? 4th sigma, right? So you're already here, like here you're talking about, if k is root 2, then you're looking at already like 4 sigma there, and here is where you've got like k square, so it's actually 2 sigma here. Okay, and each of these being an approximation to the log at that scale, right? Each of these is actually an approximation. Now what can you do? Okay, now what you can do is, you can look at, let's say, suppose I look at dog 2, right, and I want to catch extrema now. So what I can do is just the same thing, right, what I said last time. So I can look down and up, right, and I pick something here. I take a 3 cross 3 neighborhood. I take a 3 cross 3 neighborhood, up the scale, down the scale, and in that scale, right, by scale I mean in that sigma. Okay, that's why it's called scale space. Scale has to do with sigma. Space has to do with the resolution of the image. So up the scale, down the scale, and at that scale, you compare with how many neighbors? 26, right? 26 neighbors, 9 above, 9 below, and 8 around you. And then if you find that, right, you are the highest, right, in terms of strength again, right? If you find that the magnitude of the strength of this dog response, right? If the strength of this response, we won't call it log response, but it's actually an approximation to the log response. But whatever is the dog response that you get, if that strength is the highest there, then you would actually think of that as an extrema. So it could be a minima, it could be a maxima, right? Again, like I said, you could have a blob that's dark in the middle and white outside, or it could be white in the middle and dark outside. Both are blobs for us, right? And here the interpretation is not strictly in terms of a blob or something, just that the inspiration is drawn from log, but nowhere does he. It's not about, it's not specifically meant. So for example, right, if you were to ask what is the key point, then here, right, the interest point that you're trying to find out. The interest point is whatever fires up, right, under this scheme, in a sense, right? And yeah, you can think of it as blob, but it's again not strictly blob. I mean, it does fire, whenever there is a reasonable activity in this sense. Okay, but because we have seen log, we can relate to that. Okay, but then it's not like it's a blob detector or something. Okay, and okay, so what you can do is, so when you kind of compare with up and below, so you have got, right, you got to compare with, say, 26 neighbors. Okay, with this itself, right, well, you could have been happy, but actually in his paper, right, he also takes up dog 3. Okay, just to be sure that, right, if there is something, right, if you should not miss something. So he also compares that dog 3. So dog 3 will be like dog 4 and dog 2, and then he finds the extremum. But that's an implementational issue, right? How many images you take here. Okay, now it doesn't end here. Okay, this is of course one way to see how you can actually, but of course we still haven't talked about. I mean, there's still a lot more, okay, to the SIFT than this. I mean, it's not simply that that becomes the extremum. Even to declare something as a key point, right? So the key point, he actually declares that defines a certain orientation for it, which is a dominant orientation, and I mean, actually, it's a smart way of doing things, right? We'll see them one by one, but it's not over yet. I mean, this is just the extrema, right? How to find an extrema, right? We are only there as yet. The other thing that he does is the kind of speed up. For example, right? I mean, it's like, see, if you stay at the same spatial resolution, which is the highest resolution at which somebody has given you the image, and you do this, right? So what would you do? Suppose I wanted to examine, I mean, it could have structures right from small to large, right? Now, if I wanted to go to the larger ones, then I'll have to increase my sigma, right? Because that's when it will actually match up with the underlying structure. So, but then that means that you are actually operating at a spatial resolution that's the highest, and you still have to create many sigmas for that, and you have to scan through. It's almost like scanning through different sigmas to find out, to kind of locate all the interesting structures in the image. And as I said, right, you don't just show the way you still depict it as, of course, SIFT, there is a depiction which is even more interesting, but it's like saying that I found something interesting there at the center, but then I still tell that at what scale I found it. That's very important. At what scale, right? Okay, did I find it? Because when you match it, right, I mean, these things could still be important. And not only that, you want to know whether that structure is a small one or is it a big one, what kind of structure did we identify. Now, if you had to speed this up, right, what would you do? I mean, if this is time consuming, then what would be the next thing that would occur to you based upon some things that we kind of discussed, of course, not in the immediate past, but some time in one of the earlier lectures. How would you speed up? Convolution, well, convolution is going on here. I mean, that and all we are anyway doing, right? So all that is there. Okay, you will do convol in one shot. Anything else that is there anyway. What else can we do? In fact, I dropped a hint in the beginning. There is a pyramid, right? A pyramid. So what he goes for is actually a pyramid, a Gaussian pyramid.